Okay, we want to talk about Newton's law of universal gravitation, which Newton worked out to explain the orbits of the moon and the planets. Kepler and others had really good data on how the planets appeared to move. Newton put it all together. Okay, with his law of universal gravitation, and basically just it's an inverse square law. And I'm not going to tell you how Newton did that. We're going to do that from the perspective of gravitational field, flux, and so forth, because that's exactly where we happen to be in multivariable calculus. Okay. So I'm not going to go to the historical way it was developed. And I'm not going to do it with complete rigor because you're not quite there in multivariable calculus yet. Just looking at Green's theorem right now. Okay. But we understand, I hope, vector fields and flux. Okay. If we don't, that's all right. I'm not going to get too technical with the explanation, but here we go. So you've got a mass here. And it's going to be implicitly a symmetric mass. Okay, so that it acts to at any point outside the mass, it acts as if the mass was just a point mass at the center. Okay? And like the Earth, okay? We happen to be outside the Earth, not far from it, not far from its surface, you know, because it's really pretty inconvenient to get too far from the Earth's surface, because then you tend to be attracted to the Earth and you slam into the surface and it's not, and to fracture your cervical vertebra and die very quickly, okay? And otherwise, you can get internal injuries that'll kill you a little more slowly. So you don't want to get too far away without pretty good support, okay? Like an airplane or something like that, or a good solid road. Anyhow, then, okay, so here we have it. There's the Earth. It's got a mass m. Now, it's not necessarily the Earth. It's a mass m. It's a point-like mass m. Okay. It has an extent, but it acts as though it's acting from the point actually at the center of mass. So you have a gravitational field. Okay, so here's a sphere. Doesn't want to let me write an R. So I'm just not confident to write an R this morning. Okay, so here we have it. Sphere of radius R. Okay. Can you know what the area of the sphere of radius R is? One of those fundamental things that everybody used to learn before. How many of you kind of know? Let's just see. Let me just pause this thing for a second and see if anybody knows this. Put on the Zoom recording and it doesn't happen. Okay, well, anyhow. So you got a sphere of radius R. Area is proportional to R squared. Okay, so area equals KR squared for some constant K. If this was a circle, your area would be pi R squared. Turns out for a sphere, K would be 4. Okay, the surface area of a sphere is 4 times the area of a circle of the same radius. Okay. that was a little difficult to derive, unlike, let's say, the surface area of a cone, which you can snip and get the sector, spread out the sector of a circle. Okay. Anyhow, and K, I said K is 4 is 4 pi, right? Okay. 4 times the area of the circle, 4 pi r squared. We don't really need to know that. We simply need to know that area is proportional to the square of the radius. So you don't confuse this with like a 4/3 pi r cubed, which is the volume of the sphere. Okay. And something you should have integrated last week. You got to be able to do that integral. Likely to appear in the final. Okay. And do it in 3 different coordinate systems: rectangular, cylindrical, and spherical. Okay, well, all that aside, okay, here we have, and of course, I'm not talking about the physics final, I'm talking about the multivariable final. That's capital S3, whatever. Okay. So area is proportional to r squared. Now we have the gravitational field. Gravitational field is radial. Okay, in other words, if you're out here, you're going to be attracted to the center of the Earth, or the center of whatever mass this is. Okay. So we can sketch, as we did yesterday during physics class, although we did multivariable calculus, so we're doing physics today, your radial field. I'll kind of erase this like this. So you have an inward flux. If this was a fluid flowing in toward the center, like you got a container with a hole in it, and fluids flowing in toward the center, the amount of fluid that leaves here is equal to the amount of fluid flowing across the surface. Okay? Make sense? Okay. So the flux is your magnitude of your field, where F is your gravitational field, okay? It's F of X, Y, Z, although we probably do this, or F of rho theta phi. Because spherical coordinates are more appropriate because everything is spherically symmetric. Okay, anyhow, you do it in either coordinate system. Easier to do the gradient here. Gradient in spherical coordinates is a little more complicated. But integration with spherical coordinates is much easier. Okay, line flux. Okay. It's the magnitude of F times A. And it's plus or minus that, depending on whether it's an inward flux or an outward flux. Now we can put that into multivariable calculus. The flux is the double integral over the surface. We haven't done surface integrals yet. Okay, of summing up the field dotted with the normal vector. Normal vector is radial. So you just actually end up, well, we'll see in vector calculus, okay? In calculus 3 next week. We'll see how to do these intervals, surface intervals and so forth, okay? Flux equals this. On a surface where flux is constant, either inward or outward. And normal to the surface. I didn't leave myself room to write the thing. But flux is F times A. Okay. So you got F and you got the surface area, right? We conclude total flux through a concentric sphere. Now it's a concentric sphere that's outside of the mass distribution, okay? It's F times the area of that sphere, which is F times KR squared, or pi r squared if you like. Flux is the same through any sphere. If you think of the fluid analogy, if I put a sphere out here, well, anything that flows through this sphere has to also flow through this one, right? Okay. So total flux through a concentric sphere is this. Total flux is always the same. The total flux is a constant. I'm going to write it specifically C over K times 1 over R squared. It has characteristic that F is proportional to the inverse square of your distance. Okay. Now specifically, I'm not ready to go specifically, sorry. We got the specifically here. But the more mass, the more flux. Now I'm doing this in terms of flux, which is a fairly intuitive concept, okay? The more mass, the more flux. I'm not really doing the multivariable calculus. Okay, I mentioned it here, but anybody who happens to be watching this and it doesn't have a clue about multivariable calculus, you kind of ignore this, but this is all intuitive. And this is just, that's the shape of a reciprocal square graph, which you ought to know from pre-calculus in such a way that you'll never forget it. Okay, so that should be a familiar graph. It wasn't to me because I never had pre-calculus. Okay, just helped me into heavy duty theoretical calculus course. Took me all the way through multivariable calculus to understand what in the world was going on. But then I nailed it. Okay. But you know, everybody in here should have a pre-calculus course, and any pre-calculus course should make this completely obvious. Usually doesn't, even when I teach it. Okay. It should. I try to make it so. Can't get through. Okay. Other people know they're not going to get through, so they don't even try. Don't know who's right. In my opinion, you got to do it so the few students who really have the ability to go on to higher level undergraduate math get it. Okay. Applies to your teaching. Okay. Anyhow, the more mass, the more flux. Okay. Obviously, if you've got more mass here, it's like just having, well, I've got this mass and I'm going to combine this mass. Now I got a bigger mass. I've got the flux of this one and the flux of this one. When they're combined, they just add up, right? So if I have a multiple of this mass, I'm going to get the same multiple of the field. All right. More mass, more flux. So magnitude of F is proportional to mass. Okay. So you have another term in your proportionality here. And in this case, your constant C changes a little bit because of the mass. C times M is now your own C. And I'm not going to get into that. Proportionality is another thing that is not sufficiently taught to top-notch students. And it's one of the keys to understanding formulas and everything else. Really ought to make yourself a note to nail proportionality. Okay. I mean, I first started seeing it in 8th grade. Okay. And that's a puzzle over, you know, until it got formalized sometime later. By the time I graduated high school, for sure. Okay. But I still wasn't able to really use it. So it's not a simple concept. since it's not a simple concept, doesn't get hard. Except in schools that, well, some schools do. Okay. So we have this, but this is something you should understand. Now, what comes out of this the gravitational field equals this. And you know, I've been using F for the field. That looks like force. And it isn't. So I should have used something different for the field. But let's just keep in mind that this is a field. Okay. I really ought to come up with a better letter. I could change F to E, but then it would look like electric field, which has exactly the same form except for charges. So let me think about that for a minute. I really kind of want to change my name of the field because we're going to confuse it with force. Okay. I got myself in a box with F because printed F kind of invokes the idea of force, and it is a force field, but it's not a force. It's a force per unit of mass, as it turns out. And I'll explain that in a minute. But let's try this. That's a script F. That actually isn't too bad, considering I haven't written a script F in about probably 80 years. Okay. It's hard to do that. Haven't written one in 80 years. You know, I'm just approaching 40. That way. Starting to look like an F to me. I don't know about you. Okay. Of course, you don't look a bit like an F. There we got one. Okay, well, I'm going to continue this. I'm going to pause the video so you don't have to suffer through my attempts. Okay, so I think I've got all my printed F's into cursive notation. And I don't know if I got better. I kind of like this one, but I think I was writing more efficiently by the end. Used to know how to do that. Okay. So anyhow, now that's the field. And the field is actually a vector field. So I should probably put an arrow over it. Okay. Now, that field without absolute value signs of the arrow means the magnitude of the field. Okay. Means the same thing as this. Okay. Now, we'll find F by the mass m of a particle is the force. gives us the force exerted by the field on the particle. Okay. So we can say that F equals, or the magnet, well, the force, I'll just do this without the vector for the moment. Force, magnitude of the force is the magnitude of the field times m. Now, why is this? If I bring a mass in the vicinity here, like an asteroid passing the Earth or something, it's going to curve, right? Much like the steel ball did in the vicinity of a magnet, but in a much smoother and more stable way. Okay, because a magnet doesn't have an inverse square force. Okay, it actually, well, we don't want to get into that. We can model that, and we will when we get into electromagnetic field second semester. Anyhow, that's basically a particle. It doesn't have enough mass to significantly affect the motion of the Earth. Comes too close, of course, it gets captured, and then you got dinosaurs on your head. Okay, big enough asteroid. Otherwise, it just gets deflected, goes off in some other direction. Have a gravitational sling. I mean, that's what a gravitational sling does. The Earth is moving through space. The asteroid comes by the Earth and picks up some of the Earth's velocity because of the interaction with this field. Interesting idea. And we're not going to talk too much about that right now. But that's what we're talking about here. Multiply this field by the force, by the mass, and we get the force. And when we do that, the field is Gm over r squared. G looks like it. See, I know how to write a G. I don't remember having trouble with that when I did cursive, other than my handwriting was sloppy. Okay, well, anyhow, there we have it. This is the form you're going to see it in your text, if you haven't already read it. It is due until next week, I don't think so. There's a vector form. Okay. So I'm going to come up and figure out the vector form. Okay. Okay, good. Okay, now I'm posing the question, if you got a mass m, point mass at the origin, and of course that could be the mass of a planet with some finite radius, okay? Then outside of that radius, everything behaves just as though you had a point mass. Inside the radius, it gets more complicated. You drill a hole to the center of the Earth, how would your gravitational field change? Turns out it gets stronger for waves, then it gets weaker, because the center of the Earth has very high density. We'll talk about that, but not right now. So we're just trying to get the vector form of this field, okay? Now, what do you know about the field? Here's the magnitude, as we saw. And it's radial. And it's inward. So this field is radial. Inward. And inverse square in nature. So how about it? I would suggest getting a formula for any radial field. When you did the other day, or yesterday actually, or one that's maybe inward. Let's just start with that one. We can add bells and whistles to it to get this one. Okay. So give me a radial field, and then we'll see that the radial field you give me probably not going to be inverse square, but it'll be radial, might not be inward. Well, if it's outward, you just take it's negative, or it's inward. Okay. Give you that much of a hint. So just, you want to start with the field you did the other day, that would be fine. Calculate its magnitude, see, well, it's not inverse square, so now what are we going to do? Okay. And hopefully you'll figure that out. If you don't, I'll drop hints. Okay, now everybody's trying to put some stuff together. I think we've hypothesized that you got the vector xi plus yj and its radial. Okay, and got that rather quickly. Then I said, well, you had a vector right here, which is a perfectly good vector to erase, so you could do that. But this is what you want. You want an inward vector. But xi plus yj is radial, so that's still a good place to start. Now, the point is that if I want to do xi plus yj starts here and ends here, right? Now, when you're representing the vector field, of course, you want to represent the field at the point. So the only thing I would change about the picture I see is that the vector should be about this long. Okay. Okay. Roughly. And of course, you could do one down here too. At this point, xi plus yj is going to be this long, right? So clearly, since you have this circle, it's starting to erase that circle. I said, no, no need to erase it. It wasn't hurting anything. And since it's there, we might as well go ahead and do a vector here. Okay. Now we can do a bunch of xi plus yj vectors and all kinds of circles. We can see what's going to happen. They're all going to be radial, and they're going to get bigger as they go out. Okay. So that's a radial vector. And what I advise you to do was find any radial vector. Okay. Now you're getting the magnitude of that vector. Okay. That's an important thing. And it's not xi squared. It's x squared plus y squared. You can't square. Well, you can. No, you really can't square a vector. Okay, what's I times I? Well, I dot I is 1, but I times I doesn't have a meaning. It's not even defined. Okay, so you want to be careful about the details. Okay, the type of thing you're looking at. Just like if you want to tell me that the area of a sphere is some multiple of x cubed, there's something fundamentally wrong with that, right? Now you're invoking stuff that you remember that's relevant to the question. You remember something about the formula for a sphere, and it's going to be like an r cubed is going to come out for volume. Okay, if we're looking for the area, it's got to be an r squared. Okay, analogous to that, analogous to the idea that if you have an r cubed, you're going to get volume, not area, units of volume, not units of area. You can't square a vector. Okay, you can dot it with itself. You can take a cross product of it with itself. Okay. Of course, cross product vector with itself is 0. The dot product is square the magnitude. Okay, this dotted with itself gives you x squared plus y squared. Okay, so I'm going to just make a little note of that. And let this be the vector. Something you really have to totally understand because at this point in molar variable calculus, that was some covered over a month ago, well over a month ago. And you might have lost track of it. So I'm just kind of reminding you. So in terms of what you know about molar variable calculus, this was pretty well, and this does then give you, if you don't have the I and the J there, does give you the magnitude of the vector. So it's a good thing to have. Just make sure again what you write makes sense. Otherwise, can take it down the wrong path. It's confusing to you when you're trying to solve a problem. Okay. Now, confusing to me when I read it, but I recognize a lot of these things pretty quickly, and I'm not worried about that. It's if you're getting confused, then I'm worried about it. Okay. Now you taking G, you don't have to write out this. I'm not even 100% sure it's 5.7. I know it's in the negative 11. I know what the units are. But I think it probably is. So we have this. We want to get a vector whose magnitude is this, whose direction is inward. So first thing you probably want to do is find an inward vector. Okay. And to get an inward vector, well, if you multiply a vector by -1, you're going to reverse its direction. So that's going to be easy, right? So I'm going to even write that one down for you, okay? Inward radial vector. Okay. Now, the magnitude of xi plus yj, got it right there. And of course, that equals just r. Where r is distance from the origin out to whatever point. Because r is this big, so this vector is this big. When you reverse it, it's still this big. Matter of fact, if you reverse it, you represent it by an arrow from here all the way back to the center. Clearly, r. Okay, so magnitude of xi plus yj, or negative xi minus yj if you wish, okay, equals r. It's clearly not inverse square. Because an inverse square has got to be some multiple of 1 over r squared. Okay. So what are we going to have to do to this vector? And let you think that through a little bit. Okay, you got that pretty quick. That was very good. And it's a good thing because we're running out of time. We're at a matter of fact, we're out of time. We got to leave, but we'll run over just a few minutes. I'll be about to get something good here. Okay. Okay, so obviously, if you want an inverse square, now you write down r over 1 equals gm over r. You didn't really need the gm, but it doesn't hurt because you're going to have it ultimately. But that's not going to be inverse square. That's just going to be constant. Okay. If you divide by r cubed, though, you get a reciprocal square. So you get something that looks like this. Okay, so this should be the magnitude of F. Okay. So that's the magnitude of that. You have to multiply that by a unit vector in the direction of your field. Okay. Unit vector, I'll fill this in for you, but this should be second nature from multivariable calculus, okay? It's the vector over its magnitude. Right. So using this, I have to use it over here because that's where you have the blank space. But that's the way things develop when you're solving a problem. It gets all scattered, right? Then you put it into coherent form. Okay. And you see the flow of your thinking, but it's all here. Okay, so let's just in the final form. I'm going to write it this way. You'll be familiar with this notation. Your radial vector R is just a vector from here to there, right? That's your xi plus yj. That's dm over okay. This is your unit vector. A unit vector in the direction of there. I could say it's R over magnitude of R. Okay. So now this equals is a 3/2 power of x squared plus y squared instead of the cube of the square root. Okay. Inverse square inward because of minus size, excuse me, and radial, right? And now this is vector field. It's actually very simple once you think through this a few times. And now you have a little broader perspective because your textbook is just going to assert the thing, but it is going to give you, okay. Actually, it's going to give you basically this or negative GM over R cubed times the R vector. Okay. So here's your R vector. Well, actually, your R vector is here to here, so it's a negative of the R vector, which Well, you got the negative sign there. And there's your inverse square proportionality. If you got an R cubed there, it's an inverse square proportionality because one of these R's makes a unit vector out of this. Okay. Try to understand that for both physics and vector calculus. Okay. A really good example and one of your more accessible examples.